Right, hello Year 11 chemists, and welcome to this lesson. It tells you on here what we're doing. We're doing topic 9, lesson 1 on the atmosphere. Now, this is actually a lesson for my current class in Year 11, so hello to you lot. And if you've been following what we've been doing in our class at the minute, we haven't actually started topic 9 yet. So this is going to be a standalone topic, so I want you to find a new page in your book, maybe towards the back. You'll probably need to leave at least, I would say, 6 pages for the rest of topic 8. And then you're going to open your book and do a little title, topic 9. Alright, we're going to be looking at the atmosphere. And this is lesson 1, probably of 2. So I haven't got an exercise book with me, so I'm just going to crack on with this. And I'm going to pretend that this is my exercise book. And I'm going to open it up where I will find a double page, and I'm going to try and teach you what I would normally teach in 2 lessons in about half an hour. So that's the aim. What we're going to be doing in this lesson is we're going to work out what the atmosphere is like today, what the atmosphere was like at the beginning of the Earth, and then talk about how the early atmosphere became the present day atmosphere. So we're actually going to do this by constructing a timeline. This is not only going to be a lesson, it's also going to be the revision diagram that I would use. I've not actually practiced this, I've thought it through, but we're just going to draw a diagram as we go to try and get all of the information on. Little things I've got by my side, apart from a cup of coffee, I've got a GCSE revision guide in case I forget any of the facts, and I've got a few different coloured pens. So let's get going. Alright, what I'm going to do firstly is draw a line on my page where this is now the present day and this is the age of the Earth. First thing you need to know, 4.6 billion years old. Now I'm not getting into whether or not or how we know that, but this is the widely agreed scientific viewpoint on how old the Earth is. Okay, so this is an incredibly long time. Now normally in a lab I would show us sort of roughly how long this is in terms of measure out 4.6 meters, and you would see this an incredibly long time, especially compared to how long humans have been around, which is approximately the last 2 millimeters of this line. So humans have not been around here for very long at all compared to the age of the Earth. What we're going to do here is we're going to draw a pie chart and another pie chart over here. Now I'm not obsessing over these being spherical. I'm just drawing 2 pie charts, and you need to know the information in both of these. This is today's current atmosphere. So what you need to know is you need to know the percentage of the gases in today's atmosphere. So I'm going to do this. I'm going to go just over 3/4 to there, because around about 80% of the air that you're breathing in is nitrogen gas. Whether or not you knew that, or whether or not that surprises you, that is a truth. 80% of the air you're breathing in is nitrogen gas. I can't help but do this. Nitrogen with its triple bond N and other things that you know about nitrogen. It's a very, very stable gas, and it makes up 80%, or, as the examiner likes to say, about 4/5 of the air. The remainder, about 1/5 of this, so nearly the rest of it entirely, is oxygen. That is about 20%. Or about 1/5, and you need to know this information in the exam. You could probably do a bit of maths. 80% plus 20% is 100%, but there's a little bit of space left for other gases, and the other gases are about 0.9% of the air is argon, which might surprise a few of you, and about 0.04% is carbon dioxide, and as many of you know, that percentage is rising. We come on to climate change and things like this later on. It's 0.04% carbon dioxide, and it's meant to be 0.04%. So if it changes even a small amount, it has pretty serious effects. So let me be under no illusions here. 80% nitrogen, you need to know 20% oxygen, about 1% argon, or 0.9% argon, and 0.04% carbon dioxide. You need to know that, learn. So that's what you're breathing in now with every breath. We don't include water vapour in here. So H2O gas is not included. So I want you just to listen as to why that is, because the amount of water vapour in the air, there is water vapour in the air, but it changes from day to day. You will know this as like humidity. You can have very high humidity days, you can have low humidity days, because water condenses quite easily, forms clouds, forms rain. So we don't include water vapour in there, but you are breathing in water vapour. The early atmosphere was nearly entirely carbon dioxide. So I'm actually going to make this up, because you might see a diagram like this. It's nearly entirely carbon dioxide with a little bit of other gases such as nitrogen, a tiny amount of nitrogen, some ammonia, NH3, so that stinks, a little bit of methane, possibly. So you need to know that. So this atmosphere here is thought to be very similar to Mars and Venus today. So we look at the atmosphere of Mars and Venus and we think that was what the Earth's early atmosphere was like. Because special things happened on Earth that turned us from this pie chart into this pie chart. So in today's lesson, we're going to look at how we've gone from nearly all carbon dioxide and no oxygen and a tiny bit of nitrogen to nearly all nitrogen, loads of oxygen, and where's all the carbon dioxide gone? So this is what we're going to learn today. All right, everything on here you need to know, including the Mars and Venus stuff. Right, so the Earth is 4.6 billion years ago. Is 4.6 billion years old. What you need to know about the Earth's early state was that it was incredibly volcanic. Volcanoes. It was a hot Earth. And these volcanoes were spewing out lots of carbon dioxide, ammonia, a little bit of nitrogen, and loads of water vapour. This is going to come back very, very soon because it plays a very important role. So the Earth's early atmosphere, the Earth was a very, very hot volcanic rock. All right, so as soon as the Earth was formed and it was hot and volcanic, the Earth starts to cool. All right, the Earth starts cooling down in this period. As soon as it's formed, the Earth is cooling. And what happens, the significant events that you need to know is the water vapour from those volcanoes, all of that steam that comes out of the volcanoes, the water vapour, I'm just going to write it like a chemist would, H2O gas turns into H2O liquid, which in everyday language means it rains. It rains and rains and rains because the water vapour condensed. Why did the water vapour condense? Because the Earth cooled. Okay? We've got a hot early Earth pumping out carbon dioxide, water vapour, ammonia and nitrogen. It cools down and all of that steam from the volcanoes condenses. And there is enough rain there to form the oceans. That's right, the oceans on Earth were formed from the steam of the volcanoes, which is crazy to think. All right, so this is the first step that you need to know. It rains, it rains, it rains, it rains, it rains. All right, inside these oceans, very interesting thing happens. All right, a lot of our carbon dioxide is going to go into the oceans. So one thing that we need to know from this whole diagram is, where did the carbon dioxide disappear to? Well, CO2 dissolves in the oceans. CO2 dissolves in the oceans. So the carbon dioxide levels are starting to drop. They're going down from this, they're starting to drop. Okay. When the CO2 dissolves in the oceans, we just got to learn some facts. This forms carbonate precipitates. I know that's a little bit technical, but a carbonate precipitate is like something like calcium carbonate, solids start to form. Next thing that we've got, these carbonate precipitates form carbonate rocks. They form carbonate rocks. Okay, so if somebody asks you in the exam, where did some of the Earth's early carbon dioxide go? It dissolved in the oceans, it formed carbonate precipitates, and then it formed carbonate rocks. Alright, so we're here. The Earth is cooled, 4.6 billion years old. It starts to cool, it rains for an awful long time, and then this little section here you need to know, and there's going to be more of these details that you just need to know out of the blue. Alright, I'm just checking in my revision guide that I'm on track. And I am. Right then, the next thing that we need to know about is where a load of the other carbon dioxide went. And this happened at a very significant time, 2.7 billion years ago. If that's 4.6, that's about 2.3, so around about here. Very important time, 2.7 billion years. Around 2.7 billion years ago, a very, very important thing happened, and that was algae. Algae appears on Earth. Alright, it's actually in the fossil record, appearing around about this time. Algae appears, and what algae can do, you're a load of biologists, it can do photosynthesis. Alright, so algae appears about 2.7 billion years ago. I mean, you've got the perfect atmosphere for algae to appear. It's hot, it's wet, and there's loads of carbon dioxide. So algae appears, and algae can start to process this carbon dioxide. So carbon dioxide is taken in by the algae, reacts with the water with 6 H2Os, and it starts to form 6O2 and C6H12O6. Yeah, that's a biology equation, but it's also a chemistry equation. And what this tells us is carbon dioxide go down when algae appears and oxygen levels go up. The oxygen on Earth starts to go up when algae appears. So that could quite simply be shown on a graph. Now, this isn't part of the notes, but if you had a graph that was 4.6 billion years old, you would see that the atmosphere is mainly carbon dioxide. It starts to drop a bit when the oceans form, and then at 2.7 billion years, carbon dioxide levels drop quite sharply. And an examiner could ask you, what happens at 2.7 billion years? And you go, algae appears and starts to do photosynthesis. At the same time, you could draw a graph here, and then this line starts to come up like that. What does this line represent that starts to appear at 2.7? Well, of course, that's oxygen gas, which eventually levels out at around about 21% or 20%. Okay, so they could give you graphs like this. So what have we got so far then? We are moving from the Earth's early atmosphere, which is all carbon dioxide. And what we've got to describe is, where did the carbon dioxide go? Well, we've got two things already. We've got number one down here. I'll put it with this pen, nice purple pen. One, where did the carbon dioxide go? It dissolved in the oceans and formed carbonate precipitates, forming carbonate rocks. Number two, algae appears and starts doing photosynthesis. This takes carbon dioxide in and releases oxygen. Later on, around this sort of period, once we've got a lot of oxygen, so somewhere on this timeline, and I'm not going to commit to where, but somewhere down this direction, animals appear because there's now enough oxygen on Earth. Animals cannot appear until plants have made the oxygen for us. Alright then, so the last little bit that we need to know about where did the where did the carbon dioxide go? We've got dissolved in oceans to form rocks, we've got photosynthesis, and then number three, we've got this. Locked up in fossil fuels. Okay, so you need to know that some of the carbon dioxide from the early atmosphere is locked up in fossil fuels. Okay, so this is things like coal. Now, coal is formed from ancient plants like trees that took in carbon dioxide and then got buried under loads of sediments and formed coal. We've got plankton, so we've got crude oil, my bad, that we know came from plankton. And we've got also natural gas, which also comes from plankton. Okay, so 3 things: carbon dioxide dissolves in oceans, photosynthesis, and locked up in fossil fuels. There is one last little bit that I could say that, and it's a 4th, and I am going to put it on because it does appear every now and again. And it's very specifically about some animals made shells from carbonates, the same carbonates that are here. Some animals made shells from the carbonates, and they died, and they fell to the bottom of the sea, and they were squashed, and they formed limestone. All right, now if you live in Matlock or around that way, you will have seen huge cliffs of limestone, and that limestone is made of the carbonate shells of animals that were around a long time ago. So we are going to make sense of this diagram shortly, but what it's describing is, where did the carbon dioxide go? So what we've got then is our final little bit, and this is around 200 million years ago. So if this is 4.6 billion, this is around 2.3 billion, that'll be about 1.2 billion, that'll be about 600,000 years, this will be about here, 200,000 years, around about there. My maths might be wrong. 200,000 years. This is our last number that we've got to have. 200,000 years is how long the atmosphere has been stable. Okay? I think that's pretty much it. What I've done is I've covered this page. Now there are extra words in there, but I am focusing on the key ones that come up. One last thing, totally forgot. How on earth did we end up with so much nitrogen? Well, the explanation on this is not as pleasing as it used to be on old specifications. So we just say about the nitrogen, because it's so unreactive, it builds up over time, is one thing that AQA likes to say. And we can also say some ammonia from the early volcanoes is converted into nitrogen. We used to say this was done by bacteria, because it was, but you don't need to know it for AQA. So what we've got there is a diagram that hopefully takes us through that whole process. It says, what was the early atmosphere? What is the modern atmosphere like? And this section is, how did one turn into the other? Now, this is my first run through, and I'm not massively pleased with it, to be honest. So I'm a scientist, and I like to make changes. So when I'm not pleased with something, I'm going to change it. So bear with me on this, because I did say that we were going to revise it as well. So I'm going to put that to one side, and I'm going to start to draw it again. All right, so I'd like you to go with me on this. You could easily turn off the video, but I think you will miss out. I'm going to do this, and the first thing I'm going to do is I'm going to put all the numbers on. All the numbers. I mean, you can pause the video if you want, but I'm thinking, where were the numbers on here? So I'm going 4.6, 2.7, 200,000. And I promise you, I'm not looking at my other copy. I'm remembering. Okay, other numbers. I mean, I know these anyway. 80% nitrogen, 20% oxygen, 0.9% argon, 0.04% CO2. This was mainly CO2, but I didn't bother with any numbers. Now I'm going to try and do other little bits. There were 2 planets, weren't there? What were the 2 planets? Okay, you can write on those 2 planets. I'll write it now. What was in this little wedge here? So I'm thinking, what else came out of those volcanoes? Can you remember? Because I can, but I'm not doing my GCSEs. So I know that a bit of nitrogen came out, loads of water. That's good for the, that's going to make the oceans. A little bit of ammonia, stinky gas, and a little bit of methane. Okay, so now I'm just building up the same picture, but it's remembering. This is the recall bit, because I clearly already know it, and you need to learn it. All right then, so volcanoes. Volcanoes spewed out all of these gases. I don't feel like I need to draw the volcanoes again. You could do if you wanted to, but the Earth was hot. I'm going to go with hot. It then cools and then condenses. That reminds me of fractional distillation. The Earth was hot, it cools, it condenses. What does it do when it condenses? Rain. What happens when it rains? Oceans form. Alright, so got that. So we got a very, very hot early Earth and then the oceans form. Now, I'm now going to get my other sheet. I'm going to look at this. This bit feels busy to me. I don't really like it. So what I'm looking at here, from my revision point of view, I'm going to look at, there's 1, 2, 3, 4 things that I need to know, which I can put under the title, Where Did the Carbon Dioxide Go? This is me teaching you now how to revise something very quickly. Where did the carbon dioxide go? Right, I might put this here. CO2, question mark. Where did the carbon dioxide go? There are 4 things. 1, 2, 3, 4. 2.7 billion years ago, algae. What does algae do? Photosynthesis. Do you know the equation? Equation, tick. Yes, I do, sir. Or cross. No, I don't. And you practice that. 2.7 billion years ago, algae. All right, let's get it in order though. CO2 dissolves in the oceans. Well, that can only happen once this is done. CO2 dissolves in the oceans. This is the fiddly bit. Forms carbonate precipitate. I'm just going to write precips. Forms carbonate rocks. Limestone is a carbonate rock, by the way. Other little thing. Algae, CO2 dissolves in oceans. What was this one? Oh yeah, fossil fuels. So any animals or plants that appeared and then died and then got squished formed fossil fuels. And what have I got down here? Oh yeah, shells of creatures form limestone. All of these substances are taking in carbon dioxide. Remember, photosynthesis, carbon dioxide down, oxygen up. Let's just have a little look at this. Algae, you know it's me, I'm going to try and make a word out of it. Algae, fossil fuels, dissolves in oceans, shells. AF, dissolves, shells. Algae, fossil fuels, dissolves, shells. DAFs, fossil fuels is together. God, I mean, I'm almost seeing the word daffodils. I'm not, but DAFs. Algae photosynthesis, fossil fuel, dissolves. Maybe it's not shells, it's limestone. Shells form limestone. I'm going to get stuck on this. LAF, laughed, maybe. Limestone from the shells. It's not in a nice order though. Oh, I don't know. What happens first? It dissolves in the oceans. It dissolves in the oceans. Do. It then algae forms. Do. This might work. F. Do. F. Fossil fuels. Do. dissolves in the oceans, algae, fossil fuels, F, and then shells turn into limestone. Do something, you make it up. I don't know. There you go. That was my attempt. I'm remembering there are 4 things: dissolve in the oceans, algae forms, photosynthesis, do a something, algae photosynthesis, fossil fuels, and then limestone forms from shells. You get what I'm doing? Yeah, do that. I'll tell you what your challenge is after this. Right then, where did the oxygen come from? Photosynthesis. I think I know it. Oh yeah, no, I do. And then what's the significance of this date? That's how long the atmosphere has been stable. You can turn off now, or doing it again. Hang on, where did the carbon dioxide go? Limestone from shells. Dissolve in the oceans, algae, photosynthesis, fossil fuels, limestone from shells. Do I know 3 fossil fuels? Yes, I do. Do I know all the dates? 4.6, 2.7, 200,000. Yeah. Yes, I am done. Hopefully from that then, you know a little bit about where the air you breathe has come from. The oceans have come from the steam of volcanoes. The oxygen that you're breathing in comes from plants. We need to thank plants, otherwise the animals would not have appeared. I need to ask you questions on this next time I see you. What I'm trying to show you here is how to very, very quickly learn something. My diagram then became this. My diagram then became this. 80, 20, 0.9, volcanoes. I don't know. That was it. Happy feast day, everyone, because that's what you'll be doing instead of an actual lesson on chemistry. But you have to have this done for next Monday for the lesson. All right? We can't afford to be missing lessons at this point. Like and subscribe. I don't even think I'm being sarcastic. I would like you to do that. It makes me feel good because I'm putting in the effort here at 7:20 on a whatever day it is, Wednesday. So I hope you appreciate it. Okay, all the best. Bye.